My name is Haifeng Qian with IBM Research. I'll present a paper titled Measuring Graph Proximity with Blink Model. So here, proximity means relation strength between two nodes in a graph. Now, quantifying relation strength is fundamental, is important, but there's already PageRank, CAS, and many other methods. Why do we need another way to do this? So let me try to motivate this work with an imaginary challenge. Suppose I draw the graph on the left and ask people, is A1-B1 relation stronger or is A2-B2? I think 99% will say A1-B1. So I get consensus, I put in the library. Otherwise, I throw it away. Imagine I do this over and over again. I get a large collection. So the challenge is, can we design a measure, a mathematical formulation that agrees with human consensus all the time? This is harder than it looks. I'll show you examples soon. Obviously, I think I have an answer, which is the following. So I take the input graph, and I pretend that it blinks. It's a random graph where edges and nodes appear and disappear, and I pretend so even if the input graph represents deterministic relations with no uncertainty. So the probability that an edge exists is its weight. If the graph is unweighted, we use uniform weights. If the weight's not between 0 and 1, here's the transformation. So the proximity score is log of 1 minus the probability that at least one path exists from node A to node B. Very simple. This measure is directed if the graph is directed. This p-value here has many different names in different fields going back to decades, and there's some references in the paper. Now back to the challenge. Assume uniform weights in these graphs, and I would argue that for each one, the human consensus would be that AB2 relation is stronger than AB1. By the definition we just saw, Blink agrees with human intuition all the time, no matter what the edge weight is. For competitors, let's look at the first graph, for example. The difference is the crossing edge, and the shortest path and effective conductance think that the crossing edge makes no difference. Well, cycle-free effective conductance and commute time think the crossing edge actually weakens the relation, which is counterintuitive. And the other three graphs show the same thing for personalized PageRank, CAS, and the expected reliable distance. Well, for more details or for debate, I'll be at my poster during the coffee break. It's over there. Now, here's a more general example. Again, I argue that AB2 relation is perceived to be the stronger one. And again, Blink agrees with human all the time, no matter what edge weight it is. And the wide class of competitors simply cannot distinguish B1, B2. These are measures that can be computed by an iterative algorithm which updates storage per node based on neighbors. This is a wide class. It covers almost everything on the last page. So after such examples, as far as I can see, Blink proximity is the only one standing in the imaginary challenge. Now some properties. Suppose I have graph G1 connecting A and B, another graph G2. If I combine the two into a new graph, the proximity score between A and B is simply the sum of the two old scores. This additivity tells me that the Blink score is not only correct in a relative sense, it's also quantitatively meaningful. It's proportional to the amount of evidence. If the score is 10 times larger, I can say I have 10 times more evidence to support a certain relation. Then there's monotonistic property, which says if I create an edge or increase the weight anywhere in the graph, a proximity score should not decrease. Very few existing methods have these properties, and I hope by now you agree with me. This simple definition of a Blink proximity is surprisingly consistent with human intuition, and more so than many existing methods. There is just one minor problem, that the computational complexity is sharp P complete, so we can only do approximation. In the 70s and 80s, there was a large body of work to compute this P number in the context of network reliability. But if a graph is more than a few hundred nodes, the only option left is Monte Carlo, which has its own problems, as can be seen in this table. So we take the graph from 2 pages ago. We create 3 cases where the edge weights are 0.1, 0.5, and 0.9. We measure the delta in the score and we measure the error in the score and the error in the delta between B1 and B2. So we're not happy with monocolor. So in this work, we propose a new approximation algorithm. It is deterministic. It is unique in that it calculates S directly without calculating P. The first row in the table shows that we can be more reliable for this graph than a million monocolor samples for 2 out of 3 cases. Again, if you come by my poster, I'll be happy to describe the algorithm in more details. So the first experiment we ran was a replication of the 2007 Liben-Nowell and Kleinberg survey, which was predicting new coauthorship relations in archive. We compare against the best results per graph, which come from different measures with different parameters, and we're able to outperform that with a single parameterization of the Blink model. These are ROC curves on one of the graphs. Now, the second experiment, we take a snapshot of Wikipedia and try to predict new citation links between Wikipedia pages for the next 1-year period. We use the 1,000-page random training set to select parameters for each predictor and then measure their performance on 1,000-page test set. The table shows mean average precision. These are the true positive rate curves. Again, Blink is the best among these. Now, I would like to close with a thought on generalization. So in this work, we study a single event, which is that node B is reachable from node A. And we can replace that with any event in a random graph. If the graph is multi-relational, the event can involve edge labels and node types. This can lead to a variety of metrics that could be interesting in different applications. So that's the end of my talk. Thank you very much.